Okay, great. So anyway, welcome back. So, like I mentioned, today we'll talk about some lessons. Actually, one slide about lessons from the classical security, so we don't repeat the whole of last meeting. But then I also talk about the different thread models, things that we talked about before, and then jump into the discussion of quantum computer controller related security topics. So just kind of maybe one slide to summarize what we talked about: GPU, CPU, and FPGA security. I think these are some basic lessons we've learned from prior research in classical hardware and architecture security. And I think the main one is basically whenever there's sort of any resource sharing within a computer, that is going to lead to some sort of a side channel attack. So whether you're sharing something in time or space, so either if users are alternating on the same piece of hardware, or actually if users are running in parallel, maybe multi-tenancy, whenever you're sharing a cache or some other structure, there's definitely going to be side channels. So I think that's one thing to remember. And maybe right now for quantum computers, we don't really have much sharing because every user is sort of pretty much using the whole quantum computer. But as there's more sharing within the quantum computer, and perhaps already some sharing within the controllers, I think this is kind of the main way that we'll find more and more side channels is through any resource sharing within the systems. Um, the second lesson, I think maybe pretty obvious, the physical attacks, of course, exploit any code or data-dependent power or EM or other emanations. So whenever you're doing some computation, at least classically, the power consumption is sort of related either to the code or data. And if somebody can observe that, then they can exploit it. And this requires physical access, but can be quite powerful. For remote attacks, we've seen there are a lot of attacks that don't necessarily require physical access to the machine, but you're running some code on the target machine. So whenever you have a remote attack, it really means the user connects remotely and runs some software on the target machine. And then, for example, for the Rowhammer attack that we talked about, the user runs an application that constantly accesses some memory locations, and that might flip other users' bits in the DRAM. And so for these remote attacks that sort of exploit some imperfections in the system, it's I think basically either due to some physical design, like the way the DRAM is physically designed. There's it's really hard at the very small scale to isolate the different DRAM cells from each other, or at the architecture level, such as caches. So how the caches are used, or the timing, or some things, I don't, not necessarily bad design, but sort of somebody overlooked something, like if a user has access to the voltage and frequency scaling controller, they could, for example, drop the voltage and cause like a voltage-based fault attack. So these remote attacks really kind of somehow, we have these layers that everybody, the users should be at the logical layer above the ISA, but somehow they bypass the abstraction layers through one of these three means. And then another sort of lesson or kind of observation maybe is that, at least in the past, it's taken a long time to find different hardware-related problems. Like, again, caches have been in processors for a long time before. In the early 2000s, people started thinking about cache timing attacks or the Rowhammer and DRAM. And I think that the main reason is that it's not that it's hard or I don't know, it mainly is because people sort of don't think about security at design time. So something is designed, and then only later, once it's widespread use, you start thinking about security. So maybe just a lesson that, we look at things early and we think about some basic things like the power consumption or the sharing. We can find these problems quite early. And then again, we don't talk much about supply chain in this class, but I think for hardware security, supply chain attacks or backdoors or some malicious modifications of the hardware is a pretty important and big topic. But it's sort of not at runtime. So like all these physical and remote attacks are sort of at runtime once the system is already running, but supply chain attacks is really when it's manufactured. So there can be a whole class on supply chain attacks. These are maybe some lessons that we can keep in mind when we think about all the different quantum computing systems. So next, Next few slides, I'll kind of review some of the ideas we talked about, the attack surface and the threat models. And then based on that, we'll start talking about different attacks from that have been proposed or demonstrated on the quantum computers. So just again, this maybe you'll get tired of seeing this here, but basically for a quantum computing system, we keep in mind kind of the setup where you have the quantum processing unit or the QPU where you actually have the qubits. That's where you execute the computation so that you can have, of course, attacks on the QPU. But really, the quantum computer is really all the control logic plus the QPU. So you can have attacks on the controllers, which is actually what we'll talk about later today. And then these are sort of, in a classical system, all of this would be sort of in one CPU, all the controller, control, and data path. But in quantum computers, at least for now, it's really separate big pieces of equipment. And of course, there could be attacks on some other classical, coprocessors, or if people are using GPUs to optimize their other quantum circuits. And then all of these attacks are really either, physically at those at the controller or the QPU, or maybe remotely due to some users, or maybe even a malicious compiler. When we talk about the different security issues, we usually ignore the networking and kind of the classical software management in infrastructure, kind of assuming it's already secured. One small asterisk is that there is sort of might be interesting work in analyzing sort of the scheduling, or for example, if you want to find out, how many quantum computers a cloud provider has, maybe you can look at the way it schedules users to the different machines. So there might be some, or maybe you can exploit the API to learn something about the quantum computer. So I would say that, the cloud management and the networking is mostly not interesting because it's very kind of classical focused, unless you're trying to maybe reverse engineer something about the operation of the cloud-based quantum computer. But so keep this, let's keep this picture in mind. And I already mentioned also GPUs. So we didn't talk about really variational circuits, but at the very high level, there's a big class of quantum circuits where you want to, you run the quantum circuit on the quantum hardware, and then you look at the results, and then you sort of you feed it through an optimizer to optimize the parameters for the quantum circuit. So of course you can have attacks on the quantum part, but if somebody can attack the classical optimization, they can extract sort of all the information about the parameters of the circuit. So effectively, you can steal the circuit from the optimizer that's trying to optimize the parameters. Question.
Well, I was thinking about something like this, and I was like, what if an attacker could perturb your outputs? It's like we're doing you're trying to estimate the ground state of some molecule, because I know that's like some example of it wrong piece, but tweaking the cost function a little bit so you make them arrive at a different solution.
Right. So if you have something like some interaction between the quantum and the classical part, then right, if somebody modifies sort of the output of the quantum circuit, then the optimizer might optimize it wrongly, or if you let's say if you do some fault injection on the GPU or a CPU that's optimizing, maybe it puts the wrong parameters in the circuit. So yeah, exactly. Whenever if you can somehow mess up the optimization, you'll end up at the wrong circuit. So that's a really good point. And maybe you can arrive at the wrong result, or maybe you can just waste a lot of quantum resources, which will cost them money. So that's a very good observation. Yeah, so we can have these QAOA circuits, for example, that have this tight loop between the quantum and the classical hardware. Just as a continue to the brief review, we talked about the structure of a typical quantum circuit. So pretty much all the quantum circuits, follow this structure where you initialize the qubits into usually into a ground state. Then you do some state preparation to put them in the initial state. Then you do the computation, and then you read out the results. And until we have quantum random access memory, or sort of some quantum memories, then sort of all the data has to be initialized in the circuit. Maybe in the future there There will be no state preparation if the data comes from a quantum memory. But in general, this is kind of the um, a flow of a circuit. So then when somebody tries to manipulate the circuit, they could try to attack the reset mechanisms to get the qubits into wrong state, um, attack the state preparation to initialize the state in the wrong initial state, or if they're doing side channel attack, maybe extract what's the initial data, then attack the gates, either the actual gates, or for example mid-circuit measurement and the conditional gates. So for different we haven't dive deeply into these, but for different architectures, there might be different ways of attacking different operations here. And then finally, if like it was mentioned earlier, if you measure something incorrectly, maybe then the output will be fed into the optimizer and not work correctly. Or if you don't reset things correctly, then actually some of the final state will be leaked to the next user. So whenever we think about the attacks, these are sort of all the points that, and again, the attacker maybe only needs to do one thing, like just attack some of the, for example, 2-qubit gates to disable entanglement and kind of break the whole operation of the quantum circuit. And this is kind of really focusing on NISQ machines. When we think about fault-tolerant and error-corrected machines, things are pretty much the same. The only thing that the basic circuits are more repetitive because you have these syndrome measurement cycles that keep repeating themselves. So in fault-tolerant quantum computing, maybe the attacker might focus on the syndrome measurements, and that way they can try to maybe break the error correction, for example. So these are all the different kind of points that either the way you reset the qubits, which will be different for superconducting or other architectures, or the way you execute the gates on the machine. And as a continued review, so for the remote attacks, especially, we'll talk later about in later meetings about crosstalk. So in remote attacks, when different users are attacking each other, you can sort of have different scenarios of how they're sharing the machine. So I mentioned earlier, whenever there's some sort of resource sharing, there's probably side channel, but there's also there's a possibility of a fault injection. So in general, we can have sort of either single tenant scenario where the user runs on the qubits, then the qubits get reset, and then another user runs, and so forth. This is basically how the quantum computers run today. You execute your job, and then the machine gets reset, and then another user runs on the machine. Or you have a multi-tenant where basically different users are running in parallel on different subsets of qubits. And in this later scenario, you can think of if one user is running next to another user, they could try to generate some noise to disrupt so user B could try to disrupt user A, or in the opposite direction, user B could try to sort of somehow measure the noise due to the user's A operation to try to guess maybe what type of gates they're using. And not long ago, there was one research paper that exactly tried to do that, where you try to measure the noise to guess, let's say, when user A is executing like a CNOT gate, and then from that reverse engineer what circuit they're doing. And when you have the users running in parallel, different qubits might be resetting at different times if different users are using different subset of qubits. So you could imagine that maybe somebody tries to generate the noise when the qubits are being reset to fault maybe the reset mechanism. That could be another attack. And then even if you don't have sort of multi-tenancy, then you could have different users could try to do something to disable or bypass the reset. And later we'll talk about quite a few papers on side channels on this kind of attacks across users. But I think it's important to point out that right now, really no quantum computer provider supports multi-tenancy. So all the machines are pretty much just, one user runs at a time, and then they keep switching. And then sort of, people keep discussing this idea of multi-tenancy, but between, I don't know, maybe practical challenges and maybe some security challenges, it hasn't really been deployed yet. So we'll see if it will be deployed or not. Question? Yeah.
So do like tunable couplers help? But I mean, if we had multi-tenant, tunable couplers can prevent some of these attacks, but
Yeah.
as a crosstalk.
Yeah. So I think the newer tunable couplers can mitigate the crosstalk attacks. I I don't think I'm not sure there's been a specific research paper that's looked at it since the tunable couplers have been introduced. But yeah, between tunable couplers that reduce the crosstalk and between the move to fault-tolerant quantum computers, where you have this error correction, sort of this cross-user issues might become much less, or maybe are already gone. That's so I think as we will see when we discuss the crosstalk related papers now, so that they're becoming a little bit older because with the improvements to the hardware and the move to fault-tolerant quantum computers, it's less there's less noise, but also if you only have access to the logical qubits, it's harder to sort of launch some sort of an attack. So yeah, so this was kind of getting less of an issue, which might actually mean that we'll finally have multi-tenant quantum computers because there'll be less crosstalk and problems. And when this is sorry, this is a very very busy slide, but when we have the multi-tenant setup, or even single tenant, when users are alternating, at least for NISQ machines, you execute the circuit for a different number of shots. And in one case, you could have the user A executes all the shots together, and then at some point you switch to user B executing their shots together. Or you could have a scenario where you could have user A and B sort of alternate their shots. And again, today, pretty much all the quantum computers run on the basis that you execute all the shots of a user together, and then you switch to another user. But a few research papers have sort of looked at kind of the security issues. If you alternate shot by shot, on one hand you get more flexibility because you can sort of mix and match shots from different users, but then you get more problems because each possibly user A and B can sort of interfere with each other on every shot. If you just alternate user A and B just once, you run all the shots, and then you switch to user B and run all the shots, then there's really only one point of attack at the point where when they're switching. So again, the current setup is much simpler, where there's sort of one user runs all the shots and they're done. But some of the research that we'll talk about has looked at kind of all different ways of interleaving users. So these are kind of the different ways of having multi-tenancy, and they've really been explored in the crosstalk attacks. But again, it's not multi-tenancy is not available today, so it's really all emulated. Are there any questions about the different possible setups of how users can run? And then for just as an aside, for fault-tolerant quantum computers, they're really not yet available publicly. So most of the fault-tolerant evaluations are really in simulation because you don't even have enough physical qubits yet to run more than, I don't know, one or a few logical qubits at best. Okay. All right. So the next part, I want to kind of review the different thread classifications that we talked about, and I think we've beaten this to maybe a little bit to death, but really all the threads really kind of come down to either having a side channel or a fault injection. I think those are the from the hardware perspective or architecture perspective, these are really the two categories that we're worrying about. And then for side channel attacks, it's really attacks on confidentiality. You use the side channel to extract some information um, that you shouldn't have access to, and usually you use it through some weird ways like measuring power, measuring electromagnetic radiation, measuring timing, and maybe some optical emanation. So the side channels try to break confidentiality and break it by using some weird or even slow things like thermal changes. So side channels um, can be pretty slow actually, but kind of weird ways of getting information out. And then on the other hand, we have fault injection, where you basically want to change the integrity or modify something. Maybe even if you don't have access to read it, you're just flipping some bits in memory, or you're flipping some qubits in case of a quantum computer. And at least in classical computers, it's mostly focused on power, EM, or clock glitching, because most circuits are synchronous sequential circuits. So if you can mess up the clock, you can mess up the computation, or for example, heating or cooling. In quantum computers, the main way to do fault injection has been through this crosstalk attacks, but there could be other ways. So, but in the end, everything really falls into either side channels or fault injection. And then again, all these attacks can be either remote or physical. So this becomes a little bit more subjective, whether you think somebody has have physical access to the machine, or if you only give users the remote access. But I think physical can be kind of much more interesting, because you can probe or measure the power consumption, for example. But if it's in a secure data center, maybe it's less of a problem. For remote attacks, you connect to the system remotely, and then you run something on the target system to inject faults or observe side channels. And then when we talk about we talk about we talk about quantum computing, but really the targets of these side channel or fault injection attacks can be either really the classical part or the quantum part. So although we're talking about the quantum computing system, there's a huge part in terms of the controller and all the logic that manages the quantum computer. So the classical part can be the focus of the attack, which might either the digital part in the controller, or maybe the analog signals that are sent to the quantum computer, or you can have the quantum target, so the qubits themselves. So this is really the two parts, and I think I don't know, somehow maybe the more vulnerable part is actually the classical part. So the quantum computer, even though it's a quantum computer, it depends on all the classical electronics for the management, controlling the execution, readout. So at least right now, since the qubits are limited, the classical part of the quantum computer, I think, is the biggest vulnerability in these systems. So then, I don't know if it's necessary, but then when we talk about the different attacks, you could try to really very easily categorize them. Either is it a side channel, or is it a fault injection? Is it a physical, or is it remote? And does it target classical or the quantum part? So you can classify everything into these very simple categories. I think I mentioned it maybe in the previous time when talking about classical security. Sometimes you can combine the two attacks. So for example, you can use a side channel to figure out what the system is doing, and then based on that, decide when to do fault injection. So you could have a side channel attack that tells you what's happening, and then when to do a fault injection attack. And but that really is kind of like two attacks. First, you do a side channel, and then from that you do a fault injection. So you could break it down, such combined attacks into either side channel and then a fault injection attack. So anyway, yeah, everything can really fit into these simple categories. And to continue, just as a review, so we talked about different side channel categorizations and fault injection categorizations, and this is from last time we talked about the different the types, things like that. I think one perhaps important update I made here is that when we talk about side channels, it might be useful to think about sort of what is the source and what is the sink or the target. So for example, are you leaking, are you leaking information from the kernel to the application or from, from some physical or circuit to the application. So whenever you have a side channel, there's sort of the source of what you're extracting, and then or where it's being collected. So, if you have like a, if you have like a local access, then maybe the target could be a physical layer because you can collect some physical properties. If you only have remote access, then maybe the target is only the application because you're running some remote software, and that's collecting the side channel information. So I think we omitted this last time, but like differentiating the source and the target can be, I think, can be important. So so slightly updated kind of categorizations, but again, you have the type of side channel, timing power, what are you trying to leak from, who's collecting the data, what's the target, is there any sharing, is there any sort of local access, and then are you targeting the code or data. Um, um, and um, and then for FTQC, we sort of just have the small change that now the controller is not just issuing the gates and then reading out the output, but it's also doing the error correction or some error mitigation. So there's just I think it's basically the same, but you have more in the classical part. So again, the classical part of the quantum computer keeps growing, and that means that the attack surface is bigger. Um, I don't know, any questions about these parts? Okay, pretty easy. Okay, so and then we had this for the fault injection, we had this classification of again the fault target, the fault model, the fault bound, and the lifespan. So again, so what are you targeting for the fault? How what type of faults could be possible, how many there are, and then how long the fault lasts. So in the simplest case, could just one physical gate, one quantum gate could be the duration of the fault, or in the extreme case, you just damage something forever. But for the fault, I think the interesting classification is again in the controller to look at is it really focusing on the analog part or on the digital part of the controller? I think that's the kind of a uh, interesting distinction. And when we add the error correction, then basically you add more digital parts to the controller for all the error correction. So there's more more computation, more memory that you could fault. And then in terms of the lifespan, I think that now you have sort of the a new unit of time, which is the error correction cycle. So something could last for, you could fault just one gate, or you could fault, during the whole error correction cycle or multiple error correction cycles. So somehow in FTQC, you just sort of a new type of a unit for the lifespan. Yeah, so just review, but kind of yeah, remember I think for the side channels, one of the important things is sort of the source and the target. So when you're leaking, and then for the fault injection, again, what is the target, especially the analog or the digital part, or the qubits if we're talking about attacking the QPU. Okay, so hopefully that was just a quick review. Now here I added we didn't talk about supply chain, but and this is just one side, but I wanted to kind of highlight possible supply chain threats, and this is really maybe much more of a problem in the classical computers where you have many suppliers of the equipment in quantum computers. Again, there's like three companies that make the fridges and not a dozen companies that make superconducting qubits. So it's much smaller, but it's growing. And as you have bigger uh, sort of number of quantum computers, that sort of the ecosystem, I guess, is bigger, there might be some supply chain threats. And basically, the supply chain threats are about, who do you trust? Like, of course, they're users who are running the quantum programs and they're compiling them. That's sort of not part of the supply chain, but what we think about supply chain, I think the two main parts are either the cloud provider, in a way they're providing the quantum computer, or the hardware manufacturer. And then so so what does the cloud provider have access to? So for example, of course, the cloud provider might control or might compile your circuit. So even though you have a benign circuit, when you submit it to a cloud provider, there might be a supply chain, so some malicious modification that the cloud provider does, or somebody inside the cloud provider, to the compiler. So they could affect, so there could be a software supply chain issue through the cloud provider. But also the cloud provider um, controls the machine. So if the machine is on premises in the cloud, then it could modify the qubits, maybe modify the controller logic, maybe insert something between the controller and the quantum computer at the interface. So these are the kind of the supply chain. Um, they could insert something in those parts, and then on the other hand, you have the manufacturer. So if you again, if you don't trust the manufacturer, or maybe the manufacturers outsource some of the components to other companies, then again, maybe the controller that they distribute has some problems. Maybe the FPGA is compromised, or maybe they manufacture some extra circuits on the quantum chip that you don't know are there. So the supply chain really is about how the hardware could be modified, or have some extra functionality. But in part, it could also be the software, like the compiler, or the controller runs, some bit stream for the FPGA. Maybe you use it like a ARM processor on the FPGA. So some software on the controller could be part of the supply chain. Um, and then so given that these hardware or software parts could be modified, what are some different problems? So here I try to it's a busy graph, but try to kind of describe what are some potential attack vectors. So again, we can ignore the users and the quantum programs, but for example, if you have a malicious compiler, it can actually directly modify the software, or the quantum circuits here, or modify some libraries. If you have the qubit modification, the qubits could be modified, or the gate operations could be modified. So given some of the hardware is untrusted, these are all the kind of possible attack vectors. And as a again, so these are really at the manufacturing time, or when the quantum computer provider integrates um, the qubit. So hopefully this kind of, I don't know, a little bit busy, but explains the different attack vectors from, if you assume, let's say, a third party provides the controller, then for example, the controller could have some modification in the processor to um, um, capture the sequences of the gates that are executed, um, or maybe you could even amplify some power or EM signals to make it easier for somebody to measure the operation. So I don't think we're going to talk farther about supply chain, but just keep it in mind that at the end of the day, uh, whenever you're running on the cloud, or even actually on your own machine, you're not just trusting the software, but you're trusting the hardware, that somebody made the hardware correctly and that it hasn't been modified. And yeah, so any question about supply chain attacks? Again, software supply has been in the news lately with like different Python packages and then AI related software packages, but hardware supply chain, I guess, less in the news. or very rarely, but it's kind of a sort of a I think a big concern, especially for government or military applications. Um, okay, all right. So, all right, that done with the review. So, so next slides. The rest of today, I want to talk about some existing side channels in quantum computer controllers. To give an overview of what's been done on the controller side. I think the three things I'll talk about are sort of the main things that have been done with controllers so far. So uh, uh, really the work, the security work has focused either on the controllers or on the qubits or on the QPU. So today we'll talk about the controllers. So yeah, issues with the controller within our picture, and this will be mostly on side channel attacks, where you might have some physical access, and you're targeting the controller, which is the classical part of the machine. So before, just one slide talking about sort of how the controller is the interface to the quantum computer. So in the QPU, you have some inputs. So these classical inputs are encoded into quantum state during state preparation. Then the QPU does some computation. In the future, there might be quantum memory that you're reading or writing as you're doing computation, and at some point you output the results to actually get the results of the computation. So again, the quantum circuits are sent to the QPU, and until you have some quantum memory, all the information about the gates and the input data is in the input. And then again, if there's no quantum networking, all the outputs are classical, and they're sent back to the users. Currently, there's no quantum memory, no storage. In the future, could be there, and then for the computation, all the information about the computation is contained in the control pulses. So the control pulses determine what the quantum computer does, and then all the inputs come in classically, and then they're output classically until you have, quantum internet, or you have quantum memory. And then so if we remove the quantum memory, because we don't have that right now, then we end up in this with this picture where sort of the controller is like a gatekeeper to all the inputs to the machine, and then all the outputs as well. So it's really on both sides. So if you have some sort of security issues with the controller, then you either you basically know everything about what the quantum computer is doing except the quantum states during the computation, but maybe that's not really important because the valuable things are either the circuits or the. So first, just a very simple demonstration of a sort of a timing type side channel attack on the quantum computer. Uh, uh, Again, we have this. We'll see this workflow kind of a few times today. So we have the circuits that the user submits. They get sent to the controller on the actual execution on the QPU. But then for the side channels and the controllers, there's an attacker that is collecting some information. And for example, in a simple case of maybe just measuring measuring the timing of the access to the different qubits. So if the attacker can, each qubit is controlled by a separate a set of channels in the controller. So for a NISQ machine, for example, if the attacker can measure, which qubit is being actuated at what time, they will they'll see some patterns in the way the qubits are triggered, and then that might help them retrieve the user's program or some details about the user's program. So the side channel here is just observing which qubits are active at what time. And this is some small thing we did a while ago. It's maybe even too simple for a research paper, but it just kind of visually shows nicely that there's a lot of patterns when a quantum circuit executes. So these pictures are basically your This is actually from simulation. This is not from physical side channels, but it basically assumes that you have access to the when each qubit is being when a gate is being executed. So in the graphs you see the time and then which qubits are being accessed, and this is tracking 2-qubit operations. So it's each bar is like 2 qubits, and basically this we call it memory pattern, but it's really sort of timing access, and then you can see that for different quantum circuits like a quantum adder or a quantum multiplier or a quantum Fourier transform or a Trotter circuit. So these are different circuits, but they have clearly patterns in the way they access the qubits. So from if you have a database of quantum circuits and you simply measure which qubit is accessed at or actuated at what time, then you could see these patterns, and from this it becomes very clear that each circuit has a unique pattern that could be that you could pattern match. And so different circuits have different patterns, and then actually if you scale a circuit, so like let's say if you have a different size of something, if a quantum adder is adding bigger and bigger numbers, actually there's a pattern that sort of remains. Sort of the circuit gets bigger and bigger, but there's a repeating pattern. So it's kind of interesting that just by observing um, the which qubits are accessed when, you would get this nice picture of a circuit, and then you could pattern match it to some database of known circuits, and then recover what the user is doing. And then so there's some basic defenses. When a quantum computer compiler compiles the qubits, it has some freedom to assign different qubits from your program to different physical qubits. So if you randomize the assignment, then for example you could sort of break this nice visual pattern, but then that can probably still be recovered by some more advanced algorithms, or by sort of if you permute it's basically a permutation. The randomized graph, it shows sort of effectively the permutation of the first one. So visually you might be able to scramble things, but that will sort of not necessarily hide the pattern. So this is again very simple but basic kind of demonstration that quantum circuits, of course, have patterns as you would expect. And then if somebody is sitting at the controller, they can recover these patterns and then guess what the user is doing. And then maybe quantum adder versus quantum QFT is not such an interesting question, but for example, guessing whether the user is doing like some routing optimization versus running some chemistry simulation can be valuable information to you have some company that rents the quantum computer, and then the quantum computer can guess what type of business you're in, or what's your sort of secret algorithm. So even simple access to the qubits can reveal valuable information, and then so that's something you should try to randomize or protect. So just a very simple demonstration, but highlights the fact that quantum circuits have a structure, and then that could be leveraged to learn some information. So one kind of a different work. This was actually a paper from a few years ago looking at power side channels. So now looking at again the same setup, but if you can collect some information about the power side channels, you can try to recover the types of control pulses that are being executed, and then from those you could try to figure out what's the transpiled circuit, and then maybe finally what's the user's program. So here not just timing of when which qubits are being accessed, but the actual control pulses with some ability to differentiate the gates. And this is maybe a more detailed picture of the quantum computer controller. So actually what the what the controller does, it has different pulses for each gate that's executing on the quantum computer, and then those pulses for each gate are actually mixed. So there's a sort of a carrier frequency. So there's the frequency of the qubits, and you mix the control pulses with the carrier, and this is what's actually sent to the QPU. But to kind of identify the different gates, we can focus only on the control pulses, and then also when you execute the different shots of a circuit, this tries to show that you execute a set of pulses for the shot, and then there's some pause, and then again you keep executing. So you can by monitoring the activity of the controller, you could try to identify when the different shots start and end, and then also then from the pulses get this additional information. And yeah, and then each gate basically has some unique frequency and amplitude for these pulses. So that also means that the power consumption will be slightly different for each gate. And then yeah, so there's just more details about mixing the signals, and then this is the output to the qubits. And actually, in terms of the controllers, I think a lot of them are now sort of moving to an FPGA setup where or even ASIC, where all of this sort of operation is done within one FPGA or one controller. You don't necessarily have a separate signal generator and separate mixer. So really the focus of such a potential power side channel attack would be really on identifying the pulses or identifying some patterns in the pulses. And when you try to so what is some interesting things that you might try to identify. So earlier from the timing, we saw that we might be able to see some patterns that identify a type of like a QFT or quantum matter type of a subcircuit. So here, kind of more specifically, so the goals of the attackers could be something like identify the complete user circuit, basically given the knowledge of some set of possible circuits, which circuit it is. So in side channels in general, you usually sort of you have to limit your universe of things you're working with if to really get some information out of the side channel. So for the that's something like user identification, or even before I was showing this adder and QFT, you would assume you have a set of possible circuits, and then you're trying to identify which one from that set it is. So it's not like totally arbitrary circuit. It's more like you're just matching. These are the possible common circuit, which one of those it is. So it sort of constrains the problem a little bit. Another potential goal of the attacker might be, instead of identifying the circuits, to identify what's called either an oracle or an ansatz. So basically, in quantum circuits, you have a subcircuit. So it might be like an oracle that sort of repeats itself, but the parameters of that circuit can be different. So the user might want to identify the type of oracle or the ansatz in your circuit. And then this is just some examples. For example, for a Bernstein-Vazirani circuit, it's a circuit that you have the problem is basically you're trying to find a hidden substring. So you're basically the function is you're given a string of ones and zeros, and then the output is either 1 or a 0. So given you give it a string of 1 and zeros and tells you is that the hidden string or not. And then and classically, if we had a classical algorithm, then you sort of have to query it n times to try different bit positions to see if that bit is in the string. But the Bernstein-Vazirani algorithm basically lets you do it in one shot to identify the hidden substring. And then so the oracle is the circuit that implements that hidden substring. And then for the NSATs, they're mostly used in like QAOA in these variational circuits where you have a set set circuit, but you have different parameters for that circuit, and those parameters actually get optimized as you uh, as you implement the circuit. So so the user, so for like identifying the circuit oracle, the question might be, what oracle is used, what hidden substring is used, or for the NSATs, what type of NSATs is being used. Uh, so those that could be like the questions for the attacker. Other things that are possible is like identifying which qubits are being used. So called it like a qubit mapping attack. So based on the control pulses, um, identify which physical qubits are used uh, by the circuit, or kind of similar identifying the quantum processor. So each qubit and each QPU will have sort of unique control pulses, at least for superconducting qubit machines. So if from the power traces you can get some information about the control pulses, you might be able to identify which quantum computer is being targeted or is being used based on the control pulse configuration. And then the final one is the quantum circuit reconstruction. So in the user circuit identification, the idea is to match one, from a set of circuits, which one the user is using. In the circuit reconstruction would be sort of the extreme where you just totally reconstruct the circuit, any possible circuit. So these are sort of the, either identify the one of n possible circuits, identify some part like the NSATs, identify which qubits are being used or which processor, or identify or actually reconstruct the total circuit. And of course, that would be the ultimate goal always, to reconstruct the full circuit, but that might be more difficult. And then when we talk about these power side channels or other controller side channels, there's an option of, the controller drives different qubits. So you can think of about, somebody having access to information for each of the control lines for each of the qubits, which would be more powerful because you know exactly what's happening on each qubit. But since many control lines are controlled by one controller, actually measuring power or other properties of individual lines might be difficult. So maybe something more realistic is just having a total power trace across many qubits, or even something simpler, just measuring the timing that we mentioned a little bit already, or just the total energy or the mean power basically across the whole circuit. How much what's the total energy that was consumed during the execution of that circuit. And you can focus on measuring the whole circuit, or maybe just some sub-circuit, like the part that corresponds to the ansatz. And maybe I'll go a little bit faster here, but again, we have the different attacks based on either just the sort of this C here. So going backwards, so either you measure some single quantity like timing, total energy or average power, or you have more information like the trace, but the trace for power trace for the combine all the channels, or you have individual traces for the individual qubits. And I think I'll skip a little bit this part about the simulation. So far, actually, pretty much, yeah, basically all the side channel attack on the quantum computer controllers has been done by various forms of simulation. So definitely a lot of interesting sort of open questions about actually deploying this in practice. So that's one sort of one challenge. But assuming you have a sort of reasonable simulation of the power traces, I think this is actually a pretty interesting outcome. What these graphs basically show is that the error rate means how much error or noise you add to the attacker's measurement. So like when you're measuring the power, you're not going to perfectly measure the power. So you might have some error rates for the for the different measurements. But these different colors show like the time series, or basically the power time series as the circuit executes, or just the total energy or the average power, or the duration. And I think um, the the uh, the interesting part is basically that even if you look at things just as simple as, you know, the duration of the circuit, or the total energy, you can have, you know, almost 100% accuracy in terms of identifying the benchmark. So if you constrain your benchmark to a set of there's actually a QASM bench, it's a set of sort of small but common quantum circuits. Um, there, you know, even something like, you know, like duration or timing, the red line, just by looking at the execution time, you can identify the potential circuit. And then as you add more noise to this, the gate becomes harder to identify circuit, but a simple power trace over the over execution of the qubits is sufficient. So I think the takeaway message here is that you know, even something simple like total power, or sorry, average power, or the total time to execute the circuit is kind of enough to tell you which circuit of n circuits. So if it's you know, if you're choosing between like a quantum adder versus QFT, even, you know, you can just from the execution time, you can guess what it is. So kind of, you know, just something to think about, that attacker can identify the circuit by some very basic properties. And then maybe I'll skip these a little bit. There's you know, you can try to identify the circuit ansatz, or the oracle, or look at the qubit mapping. So maybe you can look at the slides a little bit later if you're interested in the details. But the main thing is that you can recover a lot of information from just some simple measurements. And for the circuit reconstruction, that's more difficult. But if you have, you know, the per channel power traces, maybe that's kind of obvious. Like if you have the information about per channel power traces, then you can basically reconstruct the whole circuit, because you can identify each quantum gate. So as you have more access, you could get to even identify the whole circuit. So if somebody develops a proprietary quantum circuit, you know, you have to think about how to protect that circuit from somebody learning you know, they cannot learn the quantum data, but they can exactly learn the instructions. And there are, you know, some very naive defenses, which are, you know, super naive, but you can, add some gates, or sort of recompile the circuit to consume more energy as it executes. Maybe add some delays to kind of make the execution time of the benchmark uniform. So there are different ways you can try to modify the circuits to kind of try to hide the properties, basically obfuscate the circuit. Although probably the ultimate solution would be some sort of, a quantum equivalent of fully homomorphic encryption. And then, these could be done sort of at the software level by, replacing some gates, or maybe even at the hardware level. I don't think I'm showing it here, but since the attack is on the quantum computer controller, maybe the controller itself could consume power or generate other emanations just to hide the signature. Okay, I only have 5 minutes, so I'm not gonna do justice to this, but very very briefly, if the previous example was on NISQ circuits, on recovering NISQ circuits, and then from the quantum gates. If we think about the FTQC for error correction, things are very similar. But for example, you can look at instead of looking at the individual control pulses, you could try to look at the activity of the logical qubits, so the whole patches of qubits. And this is again some recent work, but basically the key idea is as a quantum circuit executes now for logical quantum circuits, instead of having individual you know um, control pulses for each of the gates are changed into logical patches, and you do things like lattice surgery. But at the hardware level, within each patch, you have a bunch of quantum gates that are being activated. So as the circuit executes, you have different activity of the logical qubits, and then if now again if the attacker still is able to observe the controller or the decoder to see the activity. So again, collect something like a power trace. Instead of getting individual quantum gates, they might get the information about the activity of the different patches, and then there's some issues in recovering the which patches are exactly talking to each other. But maybe very briefly jumping to the end, similar to the NIST case, if you have a set of benchmarks or a set of known circuits, you can identify what's basically which of these subcircuits are being executed by looking at the activity of the control. So I think this was very brief, but sort of the takeaway message is that by looking at the activity of the controller, at least in simulation, already a lot of existing work has shown that you can find out which physical or logical gates are executing, and then from that you can recover some information about the type of the circuit. So this is something that should be obfuscated if you want to, let's say, hide no matter how much encryption is done in the network or in the in the cloud provider, as soon as you get to the controller, things get decrypted, you generate analog signals, and then this is where somebody can capture the power or other traces. So okay, that was rushed, but please take a look at the references or at the slides if you're interested in more details. But this kind of shows kind of the sort of the main attacks that have been proposed on the controllers. So just to quickly finish up, so we talked about reviewed the different attack surfaces, categorizations, and then talked about the controller related side channel attacks, and then next time we'll discuss the projects, but in general we'll look now kind of switch to look more on the side channels, and then more on the things that are based on the QPUs and not so much on the control. Okay, so with that, okay, let's end here.